What's up, rock stars? Welcome to another edition of Rock Stars in Math, which is you. You are the star of this show. So let's talk about it. Let's get into what we're going to be doing today. Today, we're going to be talking about modeling one-step linear equations. So we've done modeling of integers, we've done modeling of fractions. Now we're going to start working on linear equations. Could be a new concept for a lot of you, so let's make sure we really pay attention, because if we understand the modeling, we can really understand where we're going. All right, what do you get when you cross a snail and a... You get a slow poke. Yeah, that's a slow poke because a snail is slow and a porcupine has sharp needles. Slow poke. You're welcome. All right, today we're going to solve one-step linear equations, only using one variable, and we're going to do that through modeling. So that's our goal, and the main goal for us today is kind of look at how we deal with equations and thinking about what that means on a scale, because equations should be balanced, and we'll get into that a little bit. But first, we talk about vocabulary. All right, first vocabulary word that we're going to talk about is equation, okay? We're solving one-step linear equations, so it's important that we know what that word means. And so an equation is a mathematical statement containing an equal sign that will show you that two equations or expressions are equal. If you don't know what expressions means, let me just go ahead and refresh you there. An expression would be like a series of math situations, if you will, operations. So 5x, like this one, 5x plus 10, that's an expression. All right, because it does not have an equal sign. It's adding or subtracting or multiplying. It's using the operations to do a math problem, but it does not have an equal sign. That's an expression. Now, on the opposite of that is an equation. An equation does have an expression, and it has an equal sign. And on the other side, it has an expression, which is just a value of a number. So this one is 5x plus 10 equals 35. In other words, 5x plus 10, whatever that answer is going to be the same thing as the other side. They have to be equal. Real simple one would be 2 plus 2, that's an expression, is equal to 4. So this whole thing together is an equation. Okay, now next one is a term. So when we have an algebraic expression, so let's go back to expression, that is numbers with variables, which we're going to get into what that means in a second. But those are separated into terms. So I want you to look at this. One part of an algebraic expression, which may be a number, a variable, or a product of both. So here's an expression right here, okay? Expressions would say 2a plus b squared, okay? So what are the terms? All right, everything that has a 2a, everything that has an a is a term. That's a term, and this is a term because they're separated by addition sign. But also, let's go back and see what it says. It's a number or a variable or a product of both. So 2 and a is a product. That's 2 times a. Product is the answer to a multiplication problem. So that is a term, okay? B squared, that's a term. Look down here. 4x to the third is a term. 3x to the z is a term. And negative 5 is a term. That one has 3 terms. Okay, this is just vocabulary. Don't freak out if this is a little confusing. You're gonna hear a lot of it going forward. Okay, coefficient. That is simply a number which multiplies a variable. So when you're seeing these expressions or equations, you're gonna see a lot of you're gonna see things like 4x, okay, or 4x plus 7 equals 2y. Okay, and in that scenario, a coefficient is simply the number that multiplies a variable. So we see a variable, that's a variable, that's a variable, letters are variables. So this would be the coefficient because it is multiplying the x. And this would be a coefficient because it is multiplying the y. So the other examples are, here's 3x. What's the coefficient? It's 3 because it's multiplying a variable. Here we got 4y squared. What's the coefficient? It's 4. Not the 2, because that's squaring. That's not multiplying the variable. The 4 is multiplying the variable. Okay, and finally, variable, since I've said that word 32 times. A variable is simply a symbol that's used to represent an unknown quantity. So for this one, 7 plus c, c is the variable, because we don't know what c equals. That's the unknown, and that's what a variable is. D minus 4, what is d? I don't know what it is, so that's the unknown. That's the variable. And then g times 3, what's g? Unknown. variable. All right, let's talk equations. All right, so when I say the word equations early on here, I really want you to just think about an equation being a balance. Okay, if you don't know what a balance is, it's that thing where you have something like this guy you're looking at right now. You have a board going across a or a triangle right there, and the board is staying balanced. It's not leaning one way, it's not over heavy on one side, it is balanced. It's equal on both sides. And as a matter of fact, I'm going to throw an equal sign right there inside of my triangle. Okay, a balance represents whatever's on one side is equal to whatever's on the other side. So now, just like a balance, equations, when we're talking about equations, they have to keep the same value on each side in order for it to be balanced. If it's not equal on both sides, then it's no longer an equation. It's not equal. It becomes a different thing called an inequality, which we'll get into later. So how could we use this balance? All right, so look at this. Let's say I have two ping pong balls. One of them says it's worth 6, and the other one says it's worth 5. So if I just put those two on right now, I want you to imagine that balance getting heavy on the one side. All right, so then I throw an 8 on the other side, and it doesn't do anything because it's still unbalanced. What would I have to put in there in order for this to be balanced? Well, I'm asking you a question, so that must be the unknown. I don't know what that is. And some of you could look at this right now and you'd say, Tal, if 5 plus 6 is 11, so if this side is representing 11 and this side's representing 8, we need a 3 here, because 8 and 3 would equal 11. And you are correct. But for the purpose of this exercise, what we're saying is we don't know what we need to put here. And since it's the unknown, that would be the variable. So the variable will be there. So now we have an equation, okay? Because this and this have to be equal to each other. Okay, so now we're going to talk about modeling them, okay? So let's dive into this. We're going to use algebra tiles to model equations. Algebra tiles are going to be squares and rectangle blocks, okay? Every time you see a square, it's going to represent a positive or negative number. So if you see an open square, that represents 1. If you see a filled in square, that represents -1. And when you see rectangles, they're going to be our variables. So if you see a big rectangle that's open, that represents x, the unknown. We have one of those x's. And if that rectangle is filled in, that means we have a negative variable. So this would be -x. Okay, when you have that, you always have to have a key. Just like when you were modeling integers, and we use the number disks, this is what you're going to do here. So I just turn this into a key, like a map. A map tells you what all the symbols represent. Well, this tells us what all the symbols represent. Anytime I see a rectangle that's open or a square that's open, it's going to be a positive number. Anytime I see a rectangle that's filled in or a square that's filled in, it's going to be a negative number. All right, now let's get into it. All right, so let's try an addition problem. So let's say we use this key to model this equation. X plus 3 equals -5. So first of all, let's go through and look at it. We have x, that's a positive x. We have plus 3, which means we have 3 positives. And over here we have a -5, which means we have 5 negatives. So, and in the middle, we have an equal sign. So we move the equal sign down here, and now we show it. We show it through modeling. So here's what it looks like. One side is x plus 3. So I used my positive x, only had one of them because there's only one x, and I needed 3 of these because they each represent a positive 3. And on the other side, I have -5, so I did 5 of the negative squares to represent that. So what you really see here is x and 3 and -5, right? Now, that's easy to model, right? Just write that in and model it, shade it in, draw that picture on your assignment. Now we need to solve it. So to solve it, any equation, listen to me, listen. Any equation, the goal at the end of it is to get the variable by itself. In other words, when I'm done with this, I want to be able to say x equals something. So I need to get everything away from the x. In other words, isolate him, put him by himself. And to do that, you got to start moving things around. So if I want to get rid of, obviously, here's my x. I want to get rid of these 3 guys. I can't just get rid of them because then my scale will fall apart, won't it? It has to say balance. So in order for me to be able to keep my scale balanced, I have to use that whole concept of 0 pairs. So let's look and see what that looks like. So if I want to get rid of these positive 3, okay, I can simply give it its opposite. Put 3 negatives there because those will be 0 pairs, right? 1 and a -1 is 0. 1 and a -1 is 0. 1 and a -1 is 0. But Tal, you just put 3 black squares on one side. You are correct. I can't do that unless I also put 3 black squares on the other side. I'm still balanced, okay? And now what we do is we get rid of our 0 pairs. Once we get rid of our 0 pairs, we're going to have our answer. So get rid of the 0 pairs. I don't have any 0 pairs on this side. I do on this side, okay? So I'm getting rid of 3 groups of 0. So when I get rid of those, now I have x by itself. This is x. And over here, I have what's left over, which would be 8 colored in squares, which means x is equal to -8. And you have solved that problem. All right, so let's see what this looks like. What do I do to model an addition equation? So fill this in. What do I do first after I set up the model? Find out what is represented on the same side as the what. So after I draw my model, what do I do to find out? I want to find out what is over there with the variable. Okay, in the last one we had the variable, and then we had 3 of those boxes. So find out what is represented next to the variable. Okay, because we want to get rid of those guys. So let's just find out what's there. And how do I get rid of the squares on the same side as the variable? We do that wonderful thing called add 0 pairs, right? Because we want to get rid of it. So when it was an addition problem, we did the opposite by adding negatives. We added negatives in there. So then what? So when I do that, do the same thing to the other side. I just can't put those 0 pairs there. I have to add the negatives on the other side as well, which means I'm trying to keep the equation balanced. Okay. So then what? I eliminate the 0 pairs to find the solution or answer. Once I get rid of those 0 pairs, I'll have my my variable by itself, and whatever's on the other side is my solution. So just a key here, in order to get the 0 pairs, we did the opposite of what was with the variable. It was x plus 3, so we put -3 up there with it, or subtracted 3. Now let's look at a subtraction problem. We do the same thing. We look at the key to show our equations. We have x minus 3 equals -5. All right, so let's show it. We put our positive x up. This time we have -3, so we put -3 in there. And on the other side, it still shows -5. So same thing. We're trying to get that variable by itself. So we want to get this guy as our final answer. So I have -3 up there. What do? I do 0 pairs again. Addition and subtraction, you're going to use 0 pairs. Okay, so I had a -3, so I went ahead and put up a +3. And when I have that, I can't just do that. I have to do it to both sides, don't I? And this is going to look a little different than the last one, okay? Because now, once you add that to both sides, okay, so I had -3, so I added 3 to both sides. Now I have to eliminate the 0 pairs. And in this time, I have 0 pairs on both sides. So first I get rid of these 0 pairs. See you guys. And then I'm going to get rid of these 0 pairs. See you guys. And now I have my final answer. Okay, so I still have x, and it is equal to, I have 2 filled in ones, so x is equal to -2. That's that simple. Let's do some filling in the blank. What do I do to model a subtraction equation? It's going to look very similar to what we did with an addition, all right? The first thing you do is find out what is represented on the same side as the variable, all right? Remember, that is our key. The key to doing that is because we're trying to figure out what we have to get rid of, okay? So let's do that. Okay, and after that, just like addition, whatever you find is with the variable, and then the last one, it was x minus 3, we're going to get rid of it by adding 0 pairs. So we added a +3 to both sides. Okay, I have to do the same thing the other side of the equation to make sure it stays balanced. Fill that in. And then also, what? Eliminate 0 pairs to find the solution. So just like addition, very similar. Okay, well, let's try multiplication and see what's different there. Well, we have the same thing. Here's our same key. Here's our problem. Anytime you have a number, which is a coefficient next to a letter, so they're touching, that means you are saying multiplication. Okay, so we have 3x equals 9. Well, how do we show 3x's? Well, this is 1x, so there's 3 x's. Okay, and now the other side, we need to show a +9. So we're going to put 9 circles, or 9 squares there, 9 positive ones. Now, to solve, we need to know, this is a little interesting, we need to know what one of these x's is. Remember, we're trying to get to the point where we say x equals something. Right now, we're saying 3x's equals something. We just want to know what one of those x's equal. So for every x, we need to find out how many squares go with every x. Well, how many x's do we have? We have 3 of them. So we have to break our number over here into 3 groups because we want to figure out how many of them will go in each groups. So it sounds like I have 3 x's over here, and I'm breaking this into 3 groups. When I say breaking into it kind of sounds like I'm saying divide, which is the opposite of multiplication. Clue, clue, hint, hint. Okay, we need to split that up. So for every square, or for every rectangle, which means my one variable has 3 squares. Does this one have 3 squares? Yep, same thing. Does this one have 3 squares? Yep. And so what we're trying to do is, again, say how much one of them has. So 1x, which is just one of those rectangles, equals how many squares? 3. All right, what do I do to model a multiplication equation? Well, let's fill in the blanks. What do I do for each variable? All right, so in that situation, we had 3 variables. Well, we represent each one with a rectangle. And it could be filled in or left empty, depending on if it's positive or negative, okay? What do I do with the squares? I split them into equal groups, okay? I'm gonna split them into equal groups. Well, you don't really know how many groups you need to split them into unless you know how many of those rectangles you have. How do I find the answer? Well, the amount of squares, okay, the amount of squares in each group. So when I said split them into equal groups, I could split them into 2 equal groups, but that would only matter if I had 2 rectangles. I'm going to split them into equal groups based on how many of these rectangles I had, okay? Now let's try division. Okay, so we do the same type of thing. Now we have x divided by 2. And just as a reminder, anytime you see a number written as a fraction, that also means divided by. Okay, x divided by 2 equals 3. Well, how are we going to show that? Well, we put up what we see, x equals 3, but that's not true. For this equation, we only have half of one of the x's because half of an x equals 3. And again, what are we trying to solve at the end? We're trying to find out what a whole x equals. What does 1x equal? So we have 3 positive squares that only represent half of the x. Well, that doesn't work. We don't want 1/2 x equals 3. We want to know what 1x equals. So if half of an x equals 3, we need to find out what a whole x equals. Well, how many of these halves would we need to get to a whole? We would need 2 of them, okay, which means we're going to have to double everything on both sides. So here we go. Now I've doubled my halves, and I doubled the thing on the other side. So when we double what's on each side, a whole x, half and a half as a whole, equals what? 6. Okay? Because what we did basically is we had a division problem, and what do we do to balance it? We use multiplication. What does a variable represent? It represents, in this situation, a part of a whole. In division, the variable represents a part of a whole. So what do the final squares represent? Well, they represent the number in each group. Okay? And how many times do I repeat what is first represented? In other words, that first one, we had this. So how many times do I have to repeat that so that I can find my answer? Well, until all parts add up to a whole. Okay, so this one I doubled because I knew that 1/2 and 1/2 equals 2. But what if I looked like this? So now I'd have, well, that's ugly. Let me draw that again for you. What if I had this? Well, this would be 1/3, and over on this side it equals 2. Well, I'd have to do what? I'd have to triplet because I need 3 of these guys. And when I do that, it means I have to triplet on the other side too. So then 1/3, 1/3, and 1/3 equals a whole, and our answer would be 6. Okay? So what does a variable represent? Part of a whole. What do the final squares represent? The number in each group. And how many times do I do it? Until all parts add up to a whole. Okay. Okay, so I think you're just going to play with this a little bit, try to figure out if you can see how equations are balanced using a balance. And you're going to get a pretty solid understanding of one-step equations before we dive into how to do it without modeling, okay? What kind of animal will never leave you alone? The badger. He's always badgering us. Giddy up.